Okay, welcome back everyone to part 2 of this wonderful sequence of videos. So what did we do? We just finished proving our lemma. So our goal is to prove theorem 3, and theorem 3 says that C of S aligned implies E is regular flat. And to make things easier, we're going to assume that C is regular. Okay, so that's our goal, but now we've got this nice equivalent criteria. As you can imagine, we're going to prove this third one here. What we're going to do is we're going to say, let's take, so our x is now going to be E, we're going to say, let's take some point in E, and we're going to construct sort of a local section of E going through that point. So that is our goal for the rest of the seminar. So to prove theorem 3, so we're going to choose, we're going to fix some E, and so let's assume it lies over the closed point S, just to simplify. So remember, S is now this local scheme, so we're going to choose a point of E. To simplify things, let's just assume it lies over the closed point of S, otherwise we can just localize further. And then we want a section. Apparently I skipped all my last information. Oh, I just turned over 2 pages. I thought things were going very quick. I was like, I should add some more explanation here. This doesn't make any sense at this point. So I agree with my past self. Okay, so to prove theorem 3, this is our alignment regular implies flat. Okay, so to prove theorem 3, well, we're going to apply a level. We're going to pick a point, sorry, so x in E. And we want a section, sigma from S to E. So in the lemma it says we want a local section, but because S is we want a section over some open subset of S. But now because X we're assuming to lie over the closed point of S, then our open subset actually has to contain the closed point, therefore be the whole thing. So we can forget about the local section point. We want a section from S to E through X. Wonderful. So how are we going to write down this section? So remember that E is a closed subscheme of pick. So we have S to E to pick. And again, because now S is strictly Henselian local, we have a semi-stable curve. So in particular, this family has a section. So really, we can represent maps from S to this thing by line models on S. So this complet, right down here, this complet we can represent by a line model on CS. Not on S, but on CS, right? So again, there's a sort of slight subtleties about exactly what pick means, but in this situation, to write down a map from S to pick, it's enough to give a line model on CS. Well, we want this, but it's not, obviously, we can write down a trivial model, but that's not going to be useful. So we want 2 important things about this line model. We want that this induced map goes through our point little x, and we also want that our induced map factors via the closure of the unit section. And so let's think about what that means in terms of our line model L. Okay, so we want and this is going to apply some line model L on CT. And okay, so we could maybe call this map. This map is called sigma. So sigma factors via E. If and only if L restricted to CU is isomorphic to OCU. So let's think about why this is true. So here's our map to pick. Now sigma is a section, and we want it to land within the closure of the unit section. But just by the way that closures are defined, and because U is dense in S, what we want to check is that U actually is the unit, that if we restrict this map to U, it actually is the unit section. That's exactly equivalent to checking this map factors via the unit section. Okay, so we want this map sigma restricted to U to be the unit section. Well, that's just the same as saying that we want our line bundle to be the trivial bundle, or to be isomorphic to the trivial bundle. Again, saying this in further because S is local. So we want a line bundle to be trivial over U, that's one thing. And sigma goes through X. Well, I'm not sure what we can say about that really. I mean, that's the other thing that we have to worry about, I guess. So we want to write down this line bundle L, or we can think of it as being a divisor if you want. We want to write down a line bundle on L, so it's trivial over U, and such that the induced map goes through our point X. Okay, and that will then give us the flatness that we want by the lemma that I'm erasing from above. So, how are we going to construct this? Well, let's write. We're actually going to construct a divisor rather than a line bundle. Everything is going to become extremely explicit, and we're going to write down coordinates, sort of local coordinates for things, and we're going to end up writing down D, and then we're going to take L to be O of D. And so what am I going to do? I'm going to choose. So D is the line bundle we're trying to construct. Or have I done something silly?
What is T?
Thank you. There is no T.
Yes, there was
Sorry, T is S, I should say, right?
Ah, okay. Yeah.
Sorry for the confusion. Okay, yeah, so I really want to, thank you. So I just want to construct a line bundle on C, a divisor or a line bundle on C itself. So here's my S, here's my sort of E thing, here's my little X. So the basic idea, this really isn't going to work. So here's E, and here's X. So the basic idea is I want to choose a curve going through X. This is sort of my first thing. So choose a curve. So spectrum of some discrete valuation ring, say T to E through X with generic point T, eta T, line over U. Okay, so I'm just going to choose some sort of T, some T going through my point X. You could worry about whether these things exist. You should worry about whether they exist, but it is true that they exist. This is, you can deduce it from the Krull-Akazuki theorem. Generally, I mean, you want to find a curve inside some variety, so you just like slice your variety repeatedly until the dimension gets to be what you want. And then if your thing is not, maybe the curve you get, the one-dimensional thing you get is horribly singular, but you just normalize it, and then that does the job. Of course, there's some stuff to check. And of course, and also we want this sort of generic point of T to lie over U. Again, we should make sure that that's possible, but that's not so bad. Okay, so now what we can do is we can then pull back. So we have a map from T to E, and E is in pick. So we follow. So we have our map.
And you also just say that you take a test curve on S, and then this test curve is still strictly Arcadian, discrete evolutionary, right? And then that means a section through X.
Why? You don't know property. You don't have properties. I mean, how do you know that it would have been a section through S?
I mean, the restriction of my E to this test curve T.
Is not necessary. So if it's not flat, then you don't know that the generic fiber is dense. Yeah. So no, it's a very good point. So it really matters that you do it this way. The temptation is to choose a test curve in X and then try to lift it. But if you do it this way around, you find that you actually, in order to make that work, you have to assume flatness, which is what we're trying to prove. So this is bad. So what you want to do instead is to choose your test curve upstairs, and then of course you can compose to get a test curve downstairs. Okay. So here we've got a map from T to pick C over S. So this thing will give us a line bundle. So this thing we can see as a line bundle on T. So our map from T to pick gives us a line bundle on T, and we can turn that into a divisor if we want. But now we're in a very nice situation where everything is very concrete because T is a discrete valuation ring. And so we know how everything works over discrete valuation rings. So this map Does this have a name? Doesn't seem to have a name. T. So this map from T to pick gives us a line bundle L on CT Hardy divisor. So it's a line bundle, but again, we make a choice and then we get some Cartier divisor dt on CT. But now we can make them a little bit more explicit. So here's T. So notice first, so this is my CT. So notice first that CT is generically smooth. That's exactly because we require the generic point of T to lie over U, and we know that the curve is smooth over U with our assumption. On the other hand, the special fiber can be as horrible as you want. We really don't know what happens there. When we have our divisor dt, we also know that over U, over this generic point, if you like, that T lands in the unit section. So we also know LT restricted to CTU is isomorphic to O CTU because T lands in E. Okay, and so we can choose dt to be supported on the special fiber. So in other words, we can really choose our dt to be some, as a Weil divisor, it's some formal sum of these irreducible components with some integral coefficients. So we've got ourselves a dt, and ultimately the goal is to build a d here. Okay, so let's maybe recall we're doing. So we write down a Cartier divisor d on C such that, say, so here, let's call the map from T to S, let's call the map from T to S little t, and what we want is that little t up star of D is dt. So what this sort of trivial so this divisor makes 0 over U, so this divisor will, and O of this thing will give us a map to pick. Being trivial over U will guarantee that it lands in the unit section of that it lands in the closure of the unit section, and this condition is exactly what we need to make sure that it goes through X. So in some sense, this says that when we restrict to T, it really is just the map we started with from T to pick, and we already assumed the map from T to pick went through X. So that ensures that our map from S to pick will still go through little x. Okay. So if we were doing the case where the curve C was not regular, we'd have to worry about making sure that this D was a Cartier divisor, which would make life much harder, but we don't have to worry about that, which is very nice. So this is now really just a combinatorial game, in some sense, but it's a sort of fiddly one. Okay, so I drew an example there. Let me draw a simpler one so that the picture is a bit easier. My nice smooth curve.
But it's still a nodal curve, right? I mean,
Yes.
Yeah.
Yeah. I mean, it's a nodal curve, but it's maybe very singular.
Yeah.
I mean, very far from regular, indeed. But it still has a graph. Well, there are T has 2 points, the generic and the special. The generic one, the graph is just a point because the curve is smooth. So this is boring. So when I talk about the graph, let's talk about the graph over the closed point. And what's it going to look like? Well, in this case, it's got 4 points. Lines go between them. And so what we have over here, we have this divisor dt. dt divisor is a formal sum of components of the special fiber. Okay, maybe we'll call tau the closed point of t, is that reasonable notation? So really, it's like 3 times this plus 2 times that minus 1 times that. But we can really, so it's really just putting numbers in each of these things. But these components correspond to the vertices here, so we can think of it as just putting numbers on the vertices. So therefore we get a function delta t in vertices of gamma to z. So for example, if we had 3, 2, 1, minus 1, then we would not be in degree 0, so minus 2 there instead. So then depending on how my picture is a bit, so my picture should be, that's okay. So that would be minus 2 to minus 1. So this is just a divisor on the graph, if you like. It's some language that we see in the DM symposium on a regular basis. Wonderful. Okay. So, but we know a little bit, so if we start just with a function like this, so we're sort of dividing in this way, we can try to build a divisor on C which will restrict to this, and I'll talk about sort of the combinatorics behind that in a bit. But in general, that's not possible. We really need it, we have to use in a crucial way that this divisor dt is Cartier. So remember that C is regular, so like being Cartier or the divisor on C is the same thing. But this CT thing can be very singular, and so we really have to worry about whether or not this is a Cartier divisor. And so what we're going to write down is a nice condition which tells us exactly when this is a Cartier divisor. Or how we see that in terms of this function delta t. So how to see that this is okay, so note that gamma is just the graph of C by the closed point. So we already assumed that our little point, our point x lay over the closed point of S, and this thing goes through little x. So tau had better map to x. So we conclude that this tau actually lies over the closed point of S, and so particularly they have the same graph. So so we can think of it as the graph over t, but we can also think of it as the graph over this point x. So it has labels. Setting locals, we don't have to worry about this. So now, this graph, the edges have labels living in this ring here. But also, this is a graph of a semi-stable curve, so this thing also has labels. Reassuringly, these labels are closely related. So the labels of the t come by pulling back from S. I worry that this is slightly incoherent, so let me just draw a sort of more concrete picture. Okay, so this thing, maybe this edge has a label, which is some ideal A is in OS. And then over T, we end up drawing the same graph, but now the label, this is on that, T is T upper star of the same thing. Ideal in OT. Okay, so labels over S we can pull back and we get labels over T. But remember that T is a discrete valuation ring, and these labels are all just given by some powers of the uniformizer, or a uniform. Labels powers of uniformizers. So how are we going to write this? So this we saw already in Julio's talk. So Julio did something more general, that the generic fiber was not assumed to be smooth, but Julio said, okay, the label is some power of the uniformizer, but actually the label is some ideal in here, so it's some power of the uniformizer. So Julio actually labeled it just by integers, and we can do the same thing. So we can label integers. So more formally, we can sort of take the same picture a bit further, and we can take the label, the order of vanishing, and the order of pole 0 of t as well. Yeah. Okay, so for example, if this is something like k adjoin n, k adjoin a, then maybe the label here is a squared and a cubed, and then here the label just become 2 and 3. So we're just reading off these exponents as integers talk. So what's the point of all this? So in a little lemma, so dt Cartier implies that for all edges mu to b in gamma, the label b divides delta t of mu minus delta t. Okay. So this is now a completely combinatorial thing. So we have a graph, and we have on each vertex we have some integer living, and also on each edge we have some integer living. And then this thing, this sort of vertex labeling corresponding to a Cartier divisor, is exactly this condition, this divisibility condition. So for example, if this was 0, then this could be 2 or minus 2 or 4, but it couldn't be 1. Okay.
If and only if.
Yes. But I feel a bit silly because we already know this is Cartier, so it's a bit. I mean, this dt was an explicitly defined thing which we know to be a Cartier. So I should really just like. Yeah. But in general, if you just take some random divisor, then indeed this is the exact same condition for it to be a Cartier divisor. And so proving this, at least proving in particular, proving the direction that we. Proving this is not very difficult. It comes by looking. So this is a thing that you can check locally. So you look. So the local equation is given by something like xy equals a to the n. And so what principal ideals can you find? You can find principal. Let's try to draw the picture properly. So here's my. Here my gradient xy equals a to the n. So these are my 2 prime ideals. These are given by, say, x comma a and y comma a. These are given my closed things. And the divisor of x is n times x a. And the divisor of y is n times y comma a. And, sorry, this is xy. And the divisor a is xy plus, sorry, x a plus y. Okay, so this is a small computation that one should do. You know, this sort of uniformizer clearly vanishes on the whole special fiber, and it's not so hard that it vanishes once. To get these numbers out, so if you look locally at the generic point of this thing, then y is a unit, and so we find that actually locally here x is like a to the n. So if a vanishes once on here, then x must vanish n times. And so if you take if you take the linear combinations you can generate from these things, then you find that sort of you get a number here and a number here, and their difference must be divisible by n. That's sort of what drops out of this construction. It's a little bit harder to prove that that's the only possibility. So certainly these are Cartier divisors, and so if this condition is satisfied, then your divisor is Cartier. We're actually using the other implication, and that takes a little bit more work. You have to check that sort of there aren't any other Cartier.
You could also blow it up a few times, right? Until to make it regular, and then you know exactly what happened.
But is the argument to prove that easier than just doing?
I don't know. I
Yeah,
just
I
say
mean, maybe. Indeed. That's indeed another option. Yeah. You can also just blow this up and get a chain of n-1 p1s.
Then you have a regular scheme.
Yeah, and then you know that, like on each of these things, the number can change by at most 1, and will change by 1, and then you get these chains of this linear interpolation thing that Julian was doing in his talk. Okay, so our combinatorial game continues. So we turn our divisor into a combinatorial thing, just a function, and now we turn this Cartier condition also into a combinatorial thing. So notice that we haven't used yet that C is regular, or we haven't used the align condition. So we will still, we'll get to these in a little while. So we want to use this data to describe, so I realize now that it's 2:30. This seems like a terrible place to stop. If I start again next week, I'm going to have to recall all these annotations. And I could go until 3 and just try to finish this week, or I can stop and pick up. I don't know what's better. But maybe people think they want to do at 3. So I'll sit and listen to them. It's okay?
It's up to you.
Okay, well, I'll carry on for now. And then if I have to skip one line at the end, then that's not too bad. Okay, so we've converted this thing into a combinatorial data. So now we want to somehow use this data to describe our divisor D. So we want to use this data to build divisor D on C. Okay, remember C is our curve over R splitting and setting a local ring S. But the thing is that, so this divisor over a discrete valuation ring, we could specify the divisor just by giving numbers at the vertices. That was all very nice. But in general, things get much more complicated. I mean, the special fiber slot has a graph, but the irreducible components of the special fiber have much higher codimension. Over a discrete valuation ring, these components have codimension 1, so they're divisors. But in general, they have codimension, well, equal to the dimension of S. And the whole point of this is to do it when the dimension of S is greater than 1. So note the irreducible components of C bar have codimension equal to the dimension of S. So they're not divisors in general. Well, I mean, except in the boring case that we already know how it works. Okay, so that's not enough to build divisors. What I'm going to do instead is to write down a sort of set. I'm going to write down a recipe to construct certain divisors, and then we're going to use those to build up the one we want. So one way to construct divisors on C. Okay, so say the vertices of gamma we can write as a disjoint mean. We're just going to choose a partition of these vertices into 2 sets, V0 and V1, such that every edge from V0 to V1 has the same label. So here I should maybe be slightly more precise. What I mean is the same label in the local ring on S, so the label on this side in color of S. So, I mean, if my graph is sort of a very random one, then I shouldn't expect very many of these partitions to exist. On the other hand, if my graph is aligned, it somehow tells me that lots of the labels look rather similar. So the vague philosophy is that if my graph being aligned means that many more such partitions will exist. But we'll make this more precise in a little while. But for the moment, supposing we've chosen such a thing, and let's call the label, say, A.
Is this really the same label or same label of 2 taken powers?
It's really the same label, but notice that because C is regular, then if the labels are rated by the power, they must actually be equal. Because if you have something like
They are irreducible elements, right? So
yes.
So
if you have an equation like xy equals a squared, then this is not regular. So being regular implies that all the labels must be irreducible things. And so if they differ by power, if they're rated by power, they're actually equal. But you're right. That's a really important point. The same proof can be made to work in the non-regular case, but then you have to keep track of all these powers, and it's a real nightmare.
Okay, I forgot that C was right.
Yeah, but that's the simplification for today. Okay, so then